George.
Good afternoon.
Good afternoon, George.
I'm good to see Takuo. I'm looking forward to hear his presentation.
Sure. Takuo is ready, and he has sent already recorded presentation. So in 2 minutes we'll start.
Are you back to
India?
Nagpur?
Yes. I'm back in Nagpur now. I'm working here. Okay. Dennis Bilkai. Alex has also joined. Good. Hello, Alex.
Hi, Ashok.
Hello. So welcome, ladies and gentlemen, in IBAAS lecture series. And this presentation is being made by Takuo HARATO. He was working in Sumitomo, and he has developed their own technology for alumina and improvements in existing alumina technology. And he has sent us a recorded presentation. So we will run the recorded presentation. And after the presentation, Takuo is available for any questions and answers. So I request Priyanka of our office to start the presentation of Takuo. And Takuo will introduce about him in his presentation only. Okay, so welcome in the lecture series.
Okay, thank you. Please play.
Yes.
My name is Takuo HARATO. I'm very honored to make my lecture at this IBAAS 2023 technical lecture series. Today, I'll talk about the development of Sumitomo's differential extraction process and a case study for Eastern Ghats, Odisha bauxite of India and its advantages and challenges. First, let me introduce myself. I have been working for alumina industry for longer than 50 years. This slide shows my experience of developing alumina technologies. When I worked for Sumitomo, I developed some innovative processes and industrialized them. SO2 in flue gas removal using red mud is one example. We built our plant at Ehime Works for 3 boilers, and the technology was transferred to Euro Alumina in Italy. The technology was applied to boilers and alumina calciners. As for this differential extraction, I will talk in detail later. I visited Naruko in India in around 2000, maybe, when Naruko was planning the fourth digestion line. At that time, we discussed about their product, not smelter grade alumina, but specialties such as specialty alumina and specialty hydrate in order to export their product to Japan and to East Asian market. I worked for CSRO in Australia for 4 years. There, I developed a process to recover caustic soda from red mud, which process first neutralize red mud with sulfuric acid. Then the leachate sodium sulfate is split into caustic soda and sulfuric acid by membrane electrochemical processing. Then the red mud is neutralized, caustic soda is recovered to use for alumina digestion, and recovered sulfuric acid is used for neutralization of red mud. Therefore, economical neutralization of red mud and recovery of caustic soda can be achieved. I also worked for Norsk Hydro Brazil, Norte, for about 2 years and a half. This slide shows today's agenda. Aluminum is a very important material to establish the carbon neutral, sustainable society. Therefore, the raw material for aluminum production, alumina's production, must be sustainable. I know I am preaching to the choir, but I'll talk something about the sustainable issue of alumina refinery in order to introduce the necessity of differential extraction. Then I'll talk about the process and application of the process to Eastern Ghats bauxite of India, and then advantages and challenges to achieve practical use of the process will be explained. This slide shows trend of global alumina production. It's increasing very rapidly, especially in China in these 2 decades. Energy consumption is also increasing. A big problem is increasing of coal-delivered energy against the global target of zero emission in CO2. Along with the increasing alumina production, bauxite mine production is also increasing. This line graph shows the bauxite reserve life index. The life decreased from 200 years to less than 100 years in these 2 decades. Next issue is red mud storage and usage. I wouldn't need to explain these photos. A red mud tsunami tragedy in Hungary. As for red mud storage technique have been improved from pond and lagooning to dry stacking using press filters. Then it became reasonably safe, I think. But the safety is limited to mechanical and physical viewpoint. Red mud itself is still a dangerous material. We need to reduce the amount of red mud to be stored. We need to use red mud in order to establish circular economy. Many technologies to use red mud have been developed, but still barrier to use red mud is high because of big volume and soda content of red mud. This slide shows key issues towards sustainable alumina refinery. As I have mentioned so far, their energy, bauxite resource, and environment. As for energy, our target is carbon neutral. The way to zero emission in CO2 is clear. We need to use renewable energy efficiently. As for bauxite resource, new bauxite mines will be developed in future to meet the demands of bauxite. But bauxite is not an exhaustive resource. We need to process low-grade, high-silica bauxite. When a low-grade bauxite is processed, amount of red mud will increase, soda content in red mud will increase, and caustic soda consumption will increase. Then these increases impact on environment. We need bigger red mud area, and the area should be managed more strictly. Barriers to use red mud is getting higher. How to solve these issues fundamentally? One solution will be introduction of differential extraction, I think. It will reduce the consumption of caustic soda, which makes low-grade bauxite available. Red mud is split to most portion of virtually free soda and minor portion of high soda. These advantages of differential extraction will give solutions to red mud issue fundamentally, I think. Then I will explain about differential extraction. When we observe the kinetics of bauxite digestion in a conventional process, alumina and silica are fully dissolved. Desiccation is carried out after the dissolution. Red mud with this DSP is separated after the desiccation completed. Then low silica pregnant liquor and digestion residue with DSP are recovered. There are two types of differential extraction of bauxite as shown here. Because of time, I will not touch this acceleration of silica dissolution case. As for suppression of silica dissolution, there are some papers and patents disclosed as shown here. ILTD improved low temperature digestion process invented by George Bamburghi will belong to this group. Our symptom process is also belong to this type of differential extraction. In this slide, principle and key technologies for symptom process are shown. Bauxite is digested in a few minutes to extract alumina, while only a small portion of silica is dissolved. The digestion residue is separated from the sodium aluminate solution in a few minutes to avoid further dissolution of silica remaining in the residue. Then the separated silica is digested by post-desiccation. This is the principle of our process. In order to achieve differentiation of alumina and silica practically, we employed two-stream heating and a tubular digestion system. A high-rate settler was developed to separate red mud in a few minutes. Desiccation was carried out by seeded post-desiccation, and high-rate washers was also required to avoid further dissolution of silica remaining in the residue. These are key technologies for our differential extraction process. Our development started in 1990 from laboratory tests. We retrofitted a low temperature digestion plant and commissioned the plant in 1993. But after 7 years of operation, unfortunately, we stopped the operation because we are requested to change our feedstock from bauxite to smelter-grade hydrate to observe London dumping treaty. This slide shows a block diagram of our original Sumitomo process. I don't touch this slide in detail, but please remember our process after the separation of red mud, DSP. It was mixed with this red mud washing train, and for some analysis we obtained this DSP directly without mixing it. It's a very important issue. This slide shows the operation result of Sumitomo process. This column shows the operation conditions and operation result of differential extraction. This light column shows the operation conditions and operation result before the differential extraction was installed. These conditions are shown here. By the introduction of differential extraction, caustic soda consumption was reduced from 81 kg to 37 kg per ton of alumina. The reduction was by 55%. Extraction of alumina reduced by 1%, and bauxite consumption increased a little bit. Chemical composition of soda content in red mud was reduced from 8.0% to 3.7%. When the red mud was analyzed before DSP was mixed for washing, the soda content was less than 1%. After 7 years operation, we can conclude the advantages of differential extraction as follows. It achieved 40 to 60% reduction in caustic soda. Soda in red mud, virtually free soda of less than 1%. Regular maintenance was required every 3 months, especially for pressure decanters. We were almost satisfied by the process performance, but there are some defects in our process. If a process is applied to an up-to-date big refinery, liquor productivity should be improved. Seeded post-desiccation was a troublesome operation. Scaling of DSP on the first settler. In order to improve liquor productivity, ABAAS ratio of the pregnant liquor should be increased. How to raise ABAAS ratio of pregnant liquor? If we increase charge of bauxite, keeping at the same temperature, extraction of alumina will be decreased because of the equilibrium limit of solubility. If we increase digestion temperature, we need more sophisticated fast solid liquid separation. It is not practically available. Our solution is introduction of sweetening digestion. That is, first apply differential extraction to the first bauxite at extraction temperature 130 with charge ABAAS ratio 0.70, for example. After the residue separation, second bauxite is added to the pregnant liquor to raise ABAAS ratio to 0.75, for example. This introduction of sweetening digestion simultaneously solved the problem in seeded post-desiccation. This slide shows block diagrams of Sumitomo process. The above one is original Sumitomo process, and the below is Sumitomo process with sweetening. When these two diagrams are compared, these are completely safe structure. You will find that this sweetening digestion with the second bauxite replaced seeded desiccation. This sweetening digestion will be carried out at 145 or 150 degrees centigrade. By the introduction of sweetening, we will be able to get higher IBAAS ratio from 0.70 to 0.75, for example. Red mud 2 replace DSP. Therefore, this mud 2 is rich in SNA2O. This soda comes from this dissolution of silica from this bauxite and partially solved silica from this bauxite. Red mud 1 will be the same free soda as in the original differential extraction process. As for volume or weight of this red mud one, it's most part of 70 to 80%, and the rest 20 to 30% is soda rich mud. When we developed the differential process, we put priority on the reduction of caustic soda consumption. In the case, the value of the process is controlled by the price of caustic soda. Over time, I have identified strongly that the differential extraction have more important thing to establish sustainable alumina refinery. On such an occasion, I met a paper written by Ashok titled "Can India Provide Enough Bauxite to the Growing Alumina Industry?" in Minerals and Metals Review 2021. And I came up that the Sumitomo process can make a contribution to alumina industry in India. India has a big potential in the world. Then I asked Ashok to send me analysis of Eastern Ghats bauxite to carry out a case study. He kindly sent me analysis, and this table shows the data. For comparison, analysis data of some other bauxites are shown here. EG5 is considered not as bauxite, rather laterite. But I used this EG5 analysis as a gang ore to assume composite of higher silica bauxite, because these bauxites kaolinite is not so high compared to other bauxite. I extracted some data of gibbsite, other aluminas, kaolinite, and calculated the reactive silica to available alumina ratio. I will say silica alumina ratio. later. I guess this imported bauxite by India is considered as a best quality from the content of gibbsite and kaolinite and silica alumina ratio. When we compare this one and this one, EG1 to 3 are comparable to this imported bauxite. So it's a good quality. Before consideration of EG4, let's consider tromboetous bauxite first. This is an old data and this is a new one, but only available alumina and reactive silica available. From this comparison, available alumina decreases, kaolinite increases, and silica alumina ratio increases. Then their quality of MRN bauxite have deteriorated in the past 3 decades. MRN is one of the biggest exporter of bauxite in the world. Therefore, this new quality must be a standard quality in the world. Go back to EG4 sample. When compared to new MRN, gibbsite content is lower, but kaolinite content is lower, and silica alumina ratio is much better than MRN. When we consider this material from other angle, when we take average between Worsley and this one, this EG4's available alumina 38% is just the average of these two, and kaolinite is also close to average. These two. The other conclusion is bauxite is a good quality bauxite for low temperature digestion. Low temperature digestion means that other alumina's content is not so high. Therefore, it's good bauxite for low temperature digestion. I considered what are the advantages of employing Sumitomo process for Eastern Ghats bauxite. I carried out some case studies of Sumitomo process for Eastern Ghats bauxite. Process conditions and set values for study are shown on this slide. Digestion liquor conditions are here. Set values for differential extraction and sweetening digestion are here. These set values are based on our experience, as I described. But one thing I need to point out is this desiccation of 0% on differential extraction. This means that The red band one after differential extraction does not contain DSP soda in it. Benchmarks of these studies, namely I calculated unit consumption of bauxite, unit consumption of caustic soda, and unit generation of red mud 1 and 2, soda content in red mud 1 and 2. As for bauxites for the study, EG1, 2, 3, and some others are used. In addition to them, we considered composed higher silica bauxite. Ashok showed this table and figures on the IBAAS technical lecture series last year. This table taught me that when cutoff is changed, all tonnage grows triple or more. Therefore, making high silica alumina ratio bauxite. Silica alumina ratio increased from this one to this one. Making high reactive silica to available alumina ratio bauxite available is an important issue for sustainable alumina industry in India. Then high silica bauxite of this composition was assumingly synthesized from data of EZ1 and EZ5 for the following study. This figure shows the calculated result of caustic consumption by DSP formation. Here, horizontal x-axis is silica alumina ratio. The caustic consumption by DSP formation increases linearly with the increase of silica alumina ratio. When EG1 bauxite is processed by conventional process, it will 34 kilogram caustic per ton of alumina. ED2 24, and for imported bauxite it is 26 kilogram per ton of alumina. These values are comparable. When EG4 is processed by conventional process, soda consumption will be 87 kilogram. And when this bauxite is processed by differential extraction, because one case is used EG4 for second bauxite, and another case is use EG1 for second bauxite. The combination of EG4 and EG4 will need 45 kilogram of soda. This value shows unit consumption of caustic soda is reduced nearly half. When EG1 is applied for second bauxite, in this case EG4 is first bauxite, then soda consumption reduced to 36 kilogram. Another typical study is this high silica bauxite. It will consume 144 kilogram by conventional processing. But when EZ1 is applied for sweetened digestion, it will be reduced to this 54 kilogram. This consumption will be reasonable. Therefore, even bauxite with high silica and low alumina, like this one, can be processed with the combinational use of good bauxite. In this case, consumption of bauxite 1 and 2 are shown in the next slide. Consumption of bauxite 1 is 81%, and bauxite 2 is the rest of 19%. This slide shows the result of a study related to red mud. The upper part is a conventional one. As you know well, the amount of red mud generated depends on the content of available alumina. In the case of old trombetas bauxite, available alumina is 51.8%. Then the amount of red mud generated is 441 kilogram. It will increase to 873 kilogram, nearly double, by the decrease of available alumina from 52 to 42. As available alumina further decreases, the amount of red mud increases. This is one of the major effects of bauxite degradation. As for soda content in red mud, the content depends on the content of reactive silica in bauxite. It increases with increasing reactive silica. When this bauxite is processed by conventional bioprocess, we have to manage 1,313 kilogram of red mud with 8.5% of soda. This situation is a headache compared to the case of 5 processing old trombetas bauxite. But when these bauxites are treated by the Sumitomo process, the headache will be greatly relieved. Considering this worst case, if this bauxite is differentiated and the pregnant liquor is sweetened with EZ1 bauxite, then this red mud split into 2 months. Red mud 1 is 860 is about 70%, with caustic soda close to zero, virtually free soda. And the amount of red mud 2 will be 352 with 12% of soda. Then this weight, this amount is less than this one. As a conclusion, when differential extraction is employed, red mud is separated into two muds. One is low soda, virtually free soda, high in iron. The amount is most of 70 to 80%. And red mud 2 is a high soda, low iron, and more small amount of mud. Therefore, red mud will be easily used for iron industry or cement industry, even if it has to be stored at the disposal area. It will be safe to store. And as for red mud 2, it is high in soda, therefore the soda should be recovered, or since the soda is delivered from DSP, the effective use of soda light or zeolite should be considered. From the results of case studies, the advantages of this process can be summarized as follows. Caustic consumption is reduced by 50%. High silica bauxite can be economically processed. Hot precipitation is inhibited. Red mud can be separated into two muds, red mud 1 and red mud 2. Red mud 1 is characterized by content of virtually free soda and high iron, and large portion of residue is red mud 1. Red mud 2 is characterized by high soda content, and its portion is limited to 20 to 30%. Red mud 1 will find applications easily in cement industry or iron industry because of free soda, which was the largest barrier of red mud use, and management of red mud on disposal will get much easier. Disposal of red mud 2 needs strict management as before, but recoveries of soda will be much easier because of smaller volume than before. As for disadvantage of Sumitomo process is application is limited to gibbsite, the gibbsitic bauxite, and process complexity, scaling, energy consumption, and capex. These are questions than disadvantages, I think. As I have already explained, advantages of differential extraction are widely recognized, but no refineries consider to employ so far. Why? I think alumina refinery owners and engineers to be skeptical about these advantages. Can they actually realize? There are many skeptical issues, I think, and I think that as a process developer, I have to change their skeptical view for them encourage to take the risks. Here is these skeptical issues: bauxite redmond separation and washing, desiccation of seeded post-desiccation, scaling, energy consumption, complexity of differential extraction with sweetening, economy, capex, opex, and my answer to these skeptical issues are here. As for redmond separation, we developed a new pressure decanter and it worked well. In India, technology of pressure decanter is already available, but they are skeptical about separation's residence time. I will explain the phenomena or development concept later. And we already started CFD modeling for the study. Desiccation by seeded post-desiccation. Yes, it was a troublesome operation, but introduction of sweetening by second bauxite solved the problem. Scaling, no problem in tubular digestion because of adiabatic reactor. First redmond separator operated for 3 months and maintenance work was carried out, but it was a very hard scaling. How to heat the pseudo pregnant liquor to sweeten digestion will be a new challenge. I have an idea to solve the scaling problem. Energy consumption, slightly disadvantage compared to single stream digestion system. I will explain a little bit later. Complexity of differential extraction with the sweetening. Compared to single tube digestion, the process is complicated, but very similar complexity, I think, to double digestion system. Economy, plus high silica bauxite is available and caustic soda can be recovered. And another one I missed to write here is residue issue. Cons is capex. It must be a little bit expensive than single tube digestion, I think. I will explain in detail a little bit, focusing to two topics. I understand that most engineers who are specialized in solid liquid separation are skeptical about the process. Thus, the red mud can be separated within a few minutes by a volume of several hundreds of cubic meter per hour. This figure shows the concept of our horizontal shallow feed. When we carry out settling test of red mud with an addition of efficient flocculant, the mud settles down within a few minutes. We developed a new pressure decanter, and it worked well for our plant. The key is horizontal shallow feed in a pressure decanter. If we can realize this situation in an actual plant, the short settling height will be enough. Then we applied horizontal shallow feed in a pressure decanter. This is the concept of our pressure decanter. In India, I think pressure decanter is already available for double digestion. That means they already have good, efficient flocculant. In order to apply our technology to a bigger refinery, we are now considering CFD modeling and simulation. It will prove the availability of this decanter for a big refinery. Next is energy issue. Here a single stream tubular heater and the digestion system is schematically shown. The below figure is not a composite curve for pinch analysis, but shows temperature profile of slurry and steam. These values in this figure are just image. Digestion slurry enters into a heater at 70 degrees centigrade and heated to recover heat by flash steam up to 120 degrees centigrade, for example, and then further heated up to 145 by live steam. After heating, keeping for a while, and the digestion slurry goes to flash tanks to recover heat, and the flash steam heats the slurry stepwisely. This heat recovery is carried out concurrently with appropriate temperature difference. On the Sumitomo process, total heat balance in and out is the same as the conventional process, but when temperature profile is considered, in the Sumitomo process, it is a little bit complicated. We employed two-stream digestion system to achieve maximum dissolution of alumina and minimum dissolution of silica. In the case, the highest temperature was 160. To get the digestion temperature 130 at this point, then sweetening digestion will be carried out at 145 or something. This is for heating for the second bauxite. When the recovery of heat is considered, it becomes a little bit complicated because the recovering temperature at the highest is higher than the giving temperature. In this case, this giving side is this is copied here. This temperature is higher than this one, and of course this part should be used, this one, but some part will remains higher. Of course, we can get more good composite curve, but if we apply recovered steam by mechanical compression, then we will be able to achieve more energy efficient refineries, I think. As for mechanical vapor compression, Sumitomo already used the technology for evaporators. It's a very efficient, energy efficient evaporator system. In this slide, challenges to introduce Sumitomo process in India are shown. I believe that the introduction of Sumitomo process for easy bauxite is promising. First, laboratory digestion test of differential extraction and sweetening to find optimum digestion conditions is required. Second, laboratory setting test to find a good flocculant. But as for flocculant, I think in India you will already have good one. Evaluation of the two resultant residue, red mud 1 and red mud 2. The evaluation of residues, red mud 1 is close to free soda, and red mud 2 is high in soda, is very important to study the feasibility of the introduction of differential extraction. Conceptual design of Sumitomo process for Ghats bauxite and others, and then estimate of capex or opex, study of cost-benefit analysis. As conclusions of my today's lecture, first, my answer to Ashok is yes, India can provide enough bauxite to the growing alumina industry in India. Sumitomo's differential extraction process with sweetening digestion is useful to process Eastern Ghats bauxite. Even high silica portion will be economically processed. The resulting red mud can be separated into two residues of virtually free soda and high soda, and it will help to solve red mud issues fundamentally. The process will be applied to the existing low temperature digestion plants by retrofitting. Thank you for listening my lecture. I am very happy if someone is encouraged to consider the process. I will spare no effort to provide support towards sustainable alumina refinery in India. Thank you again.
Thanks, Takuo, for interesting presentation. Unfortunately, sound was a little low, but it was quite clear. And now it's open for discussion, and you are welcome to ask question to Takuo HARATO. Please.
Please.
George, Alex. Sound, please.
Yeah, I would like to congratulate Professor Harato on a very good presentation, very informative. I have a question. I guess probably the best application of this differential extraction method, like you mentioned, will be for bauxites that are very high in silica. The conventional way to handle bauxites with high silica is typically to wash out the silica, so to beneficiate the bauxite. And that also involves some capital expenditure. So I guess the differential extraction process also requires some capex to make it happen. So the question will be, what is the comparative cost between the differential extraction and the beneficiation in terms of the capital expenditure required to make it work? In your opinion, which one is less capital intensive?
Thank you very much. Thank you. Good questions. But I've never compared between differential extraction and beneficiation of bauxite. But I think beneficiation will not so expensive. But nowadays, when you make beneficiation, and then it requires big areas of deposit areas. So comparison of cost, including that areas, I think it will be comparable, or differential extraction may be economical, but I'm not sure.
May I ask, clarify this thing? Actually, Alex, for beneficiation, it is wet beneficiation process. And wet beneficiation process requires a lot of water, which is sometimes not available at the mining site. So wet beneficiation is not always working because of the shortage of water, shortage of other things. And second point, you see even Trompetas bauxite is washed bauxite, but they are not able to reduce silica content below 5.5 or 5%. So there is a limitation also in washing circuit. You cannot reduce silica like 2% or 2.5%. It's very difficult in normal bauxite. So there is a limitation in wet beneficiation process, and dry process cannot bring down silica content below 4% or 3%. It's becomes very difficult, particularly those bauxite which are high silica bauxite, like Sierra Leone bauxite, like Trompetas bauxite, and others. So there's just clarification. Okay.
Yeah.
George.
Yeah.
Well, thank you, Harato, Takuo, for this presentation. There were really interesting aspects of your process. Just a few remarks. You mentioned that a constraint or difficulty that it can be applied only for the gibbsitic bauxite. Looking at the numbers that roughly 90% of the world bauxites belong to the gibbsitic bauxites, I don't think that is a real constraint. And another one, you mentioned that the beginning, when you compared the conventional process with the original Sumitomo process, the same A to C ratio for these two processes. It means that I suppose that there were significant reserves in the A to C ratio originally, because you decreased the digestion temperature. It means that the solubility of alumina is less at lower temperature. Therefore, it means that if you used the same difference from the equilibrium solubility, in that case, at the lower temperature, the liquor productivity at lower temperature would be less. The third, maybe it's not definitely is not targeted you, but I encourage the managers of India, Guinea, wherever the world, to set up a pilot plant facility, because your process, my process, other process, I believe, require affordable pilot scale facility. That's it. Thank you.
Thank you, George. And as for the ABC ratio, in our original case, we employed about 0.69 or 0.70, and it was achieved by at 150 degrees. But when we employed differential extraction, our digestion temperature reduced to 130, but that same A by C ratio was achieved. We were satisfied at that time, and because our A by C ratio of spent liquor was very low compared to the conventional process, because our products were fine particle size hydrate, or many products we had. And we didn't want to change liquor conditions. So we employed 130, and A by C ratio point we kept A by C ratio 0.70. But when some refinery contacted us, they said that A by C ratio or liquor productivity is not enough to employ them. So we started to consider sweetening digestion process. That's our history. Thank you.
Thank you.
Any more questions?
Well, just also a comment on my earlier question about capital comparison between the method and beneficiation. I guess, like Ashok, you rightly pointed out, like they say, it's horses for courses. So there might be some situations where certainly this extraction, a differential extraction, will be suitable. At the end of the day, it's going to boil down to the economics as well as the sustainability issues in that particular area where, this alumina refinery is situated. And like you rightly say, the water requirements, the environmental requirements, the energy requirements, all this will play into your assessment of which of these two methods will be more suitable. So yeah, it's not like it's a given that it can be applied everywhere, but it definitely will apply in some situations, like you mentioned, where sustainability factors just dictate that this is the method to be applied. I guess that is the point I wanted to make.
Yes, very correct. Very correct.
Okay.
Yeah.
Water issue is very important nowadays. Yeah, thank you.
Exactly.
So please, anybody from Hindalco or Vedanta, please welcome to ask question. Vedanta, Rosalind was there. Please ask questions. Rosalind. Anybody else? Sanjeev Roy. Vijay Kumar. Anybody wants any more questions? Is there, please? Yeah, Sanjeev Roy. Very good. Your microphone.
Yes. Professor HARATO, it is a good evening, and it is really pleasant to listen to you again. I had met you long back in Nalco when you visited. But have you estimated till now the cost part, the product which will come out from this DX process?
So, sorry, I don't understand your question. Will you repeat again?
The DX process, whatever product the metallurgical grade sandy alumina, what will produce, what is the expected tune of the cost of production?
I think that even if we did made specialty aluminas, but of course, pregnant gas composition is the same, so it doesn't change sandy aluminas or specialty aluminas, I think. And I think that in Nalco, they are processing at atmospheric digestion temperature, so it will require some retrofitting to employ process, but I guess it's not so it's not so difficult, not so expensive digestion process, because residence time of digestions or residence time of separators are very short. So I guess it's not so expensive retrofitting, I guess.
Okay.
Is it okay?
It's okay, but my question was, what will be the cost of differential cost of production? What will come out by retrofitting?
Sorry, I don't understand well. My English is not so good. So, what is the cost? When
That by retrofitting, whatever additional production we will get, the overall the impact on the cost of production, what should be? What is expected or estimated by you?
Sorry, I cannot say the value. When we introduced our process, it's very small capital costs. Sorry, but I cannot say now.
Okay. Thank you. Thank you very much for your process.
Yeah. And if you need to consider to employ, and then I will be able to help you to consider basic studies.
Okay. The presentation of Takuo HARATO will be available on IBAAS website, and his email address is also there. So anybody who wants to directly interact with Takuo HARATO is welcome.
Yes.
Yeah. So any more questions? Anybody from Hindalco? And Vedanta? Okay, thanks, Takuo Harato, for interesting presentation. And we will advertise this, put it in on the website, and anybody interested, they can directly interact with you, or we can have another kind of session if there is a lot of interest coming from the industry. Thank you very much. Thank you, everybody, and welcome. And there will be 2 more presentations are lined up. One is in the month of May, in April and May, and our Alex is also going to present one of the paper. Alex, please send your topic. Okay.
Thank you for inviting me to the lecture.
Okay, this is Rosalind is there online. She is from Vedanta. I am unable to unmute. I shall ask on mail. Okay. Rosalind, she is the chief of R&D in Vedanta Alumina Refinery at Lanjigarh, and she wants some question, but she is not able to unmute her laptop. I'm not sure what problem she has. Rosalind, please try once more. Rosalind? Okay, she says that she will correspond with Takuo by email.
Yes, please. I'm waiting. Yeah.
Yeah, she is from the Lanjigarh Alumina Refinery, and she will correspond with Takuo. And if you want, you can also correspond with George, because both the technologies are almost similar with small changes, a small difference. And what George has correctly told, it is necessary for India to set up a pilot plant to test these processes, because more of the Eastern Ghats bauxite will have high silica. Now, I know the existing mine of OMC now is producing 5%, 6% silica. We have to use that, and there's a 20 million ton or 30 million ton or kind of resources of high silica. And all the Eastern Ghats bauxite deposits have low silica and high silica bauxite. So it will be necessary for India to look into these processes, because that will only save their caustic soda consumption. And when you have only 30, you can blend with high silica, low silica, and make it around 5% silica and employ this kind of process. Because making wet beneficiation plant does not make sense all the time because of shortage of water and other facility at the mine site. Thank you very much, Takuo. Thank you, George. Thank you, Alex, everybody, and Mr. Sanjeev Kumar. And hopefully we'll have, you will participate in future conferences, and also you will get the series of questions from India. Thank you very much. Thank you, everybody.
Thank you very much. Thank you. Goodbye. I'm waiting your questions.
Bye. See you.